Hello everyone. Jai Hind to all of you. Myself Dr. Ajay Pratap Singh, and I am associate professor in Department of Mechanical Engineering at Ajay College, Ghaziabad. I am teach here basically the B.Tech final year subject, B.Tech third year students. Basically, you can say theory of machines. And the last lectures I have discussed the acceleration of the linkage. In previous lecture, earlier we have discussed the velocity. So, in continuance of this, come to the acceleration of the slider crank mechanism. So, slider crank mechanism, the 4-bar mechanism, you can say that one is the sliding pair, other is the turning pair. So, you can see in this figure, uh, the crank OB makes an angle theta from inner dead center and which rotates in the clockwise direction, and the fixed point O with a uniform angular velocity with omega radian per second. So, velocity of B with respect to O or the velocity of B, because O is the fixed. So, you can represent velocity of B or the velocity of B with respect to O, that is omega into R in the normal formula. So, we can see omega BO into OB, that the acting tangentially at B. So, we know that there are the centrifugal and the radial acceleration B with respect to O, because O is the fixed. So, that the equation becomes, you can say, that the angular radial acceleration. So, ARBO, yeah, acceleration of AB equal to omega square BO into OB, and at the point of the end, suppose a point at the end of the link which moves with the constant angular velocity has no tangential acceleration, right? At the point, always remember, at the point at the end of the link which moves with the constant angular velocity has no tangential acceleration. So, draw the acceleration diagram, and you can discuss one by one step. So, you can see here that the 4-bar mechanism, that the slider crank mechanism. So, you can that the fixed point O omega, that is the OB is rotated the omega angular velocity, and that the point is the slider, and the velocity of B with respect to A, velocity of B with respect to O, or you can say velocity of B, because O is the fixed, right? And it makes an angle from the IDC, that angles become a theta, right? So, draw the vector O dash B dash parallel to BO with set of the equal magnitude with some suitable scale, and we can see here that O dash B dash, draw the O dash, you can see that is draw the O dash B dash with some suitable scale, right, because we have the known. So, from the value, so the B and from the B dash we can draw the B dash x. B dash x is the parallel to BA. So, it is known as the represent the radial component of the acceleration of A, and which represent that the acceleration of radial component A R AB is equal to velocity of BA square upon length of ABA, right. So, since B moves with the constant angular velocity, therefore, there will be no tangential component of this acceleration. So, you can draw here that O dash x, O dash B dash, that is the angular acceleration of AB. After that, B dash x, that the radial acceleration of A with respect to B. From x, again you can see here that from x, right, from x draw the vector x A dash parallel to B dash x or AB. So, these vector x A dash, these vector x A dash represent the tangential component acceleration with respect to B, that is ATB. So, from x we can draw the perpendicular to this. So, these are link AB, right, this is the link AB. From x draw the perpendicular to x A dash, these values represent acceleration of tangential acceleration of A with respect to B, and these value represent that is the tangent, this value B dash x is represent the radial acceleration, and x A dash represent the tangential acceleration. Note, suppose when always remember, when a point moves along a straight line, it has no centripetal or radial component of the acceleration. So the point A reciprocate along the AOA, right? Point A, the slider always reciprocate along this AOA, right? So it intersect, we can see x dash. So since the point A reciprocate along the AOA, and therefore the acceleration must be parallel to the velocity. Therefore from O dash, draw the O dash A dash. O dash is a parallel to A that intersect the vector x A dash at A dash point, right? So these line that is draw the A dash O dash, because the slider moves along this, so there is no centripetal force, only the acceleration must be parallel to this velocity. So from x dash O dash, draw the line and intersect at point x A dash, right? So at point A dash, so you can draw here from O dash to A dash, and these intersect at that point that is A dash. So this is the complete acceleration diagram, and now the acceleration of piston of slider A and tangential may be measured through the scale. So we can measure this value, acceleration, tangential acceleration we can measure, right? We can measure the acceleration of slider of A. So we can find out. In summarize, we can say that take the some suitable point O dash, from O dash to B dash, draw the radial component or the radial component, right? So acceleration, so that B dash will come from B dash to X dash, that the tangential, that the radial acceleration of this link AB. After from X to A dash, that the tangential acceleration, and perpendicular link AB. After that we have come to the point A dash. So from A dash, that from A, that is no the radial component, the centripetal radial component, it moves along the A way, and that draw the parallel line. So from O dash to A dash, intersect at the point A dash, and that you can measure this value is known as acceleration of A, and this value is acceleration of A, tangential acceleration. So you can calculate measure and draw this, right? So from any point you can see that, and any point in the point in between the E, right? So we can find out the acceleration of AB in such case. So same ratio, same divided in the vector in the B dash A dash at the E point is the same ratio, and E divides in figure. You can see in this figure. So A dash E dash, A dash E dash upon A dash, B dash will A upon AB, and we can find out according to that. So if any point in this, so you can calculate and find out in same ratio. Now I'll discuss here the one exercise, so you can clear basically how to draw. So the crank and slider mechanism rotate in the clockwise direction at a constant speed of the 300 rpm, and we can say the crank is 150 mm and the connecting rod length is given the 600 mm long, and they determine the linear velocity, acceleration at the midpoint of the connecting rod, and second is the angular velocity and angular acceleration of the connecting rod at the crank angle of 45 degree from the IDG center. So first of all, you draw the slider crank mechanism. So we can draw here O to B, that is the crank slider crank mechanism, clock is rotate 300 speed NO diya, and then 150 rpm, 150, and after that the connecting rod, the length is the 600 mm. This is the slider A, right? Here the slider, and this is rotate in clockwise direction with NBO equal to 300 rpm. NBO equal to 300 rpm. So NBO is the 300 rpm, and this angle is inclined and in the center is 45 degree, right? And in between some midpoint, that D point is there. So you can find out the acceleration of this link AB BU, we can determine there are two things. First one is linear velocity and acceleration of the midpoint of the connecting rod, and second one is the angular velocity and angular acceleration of the connecting rod at the crank angle is 45 degree from IDC. So acceleration crank, you can find out here that angular acceleration B with respect to O is given is 300. So we can calculate convert in the omega 300 rpm. So omega equal to omega BO equal to 2 pi n upon 60. So put the value of n. So 2 into 3.14 into 300 divide by 60, 5 times कट गया 10, 30, approximately it becomes 31.42 radian per second, and the length of OB is given. So velocity of B with respect to O equal to velocity of B with respect to O equal to omega BO, omega into R, basically you can say that is OB. So you can say that is 31.42 radian per second into 0.15 meter per second. So we become that is 4.713 meter per second, right? So we can calculate and find out. So first of all, find out the velocity. So you can see that the velocity in the clockwise direction, that is velocity of B with respect to O. You can say the velocity of VA. So the linear velocity, you can say, at the midpoint of connecting rod. So first of all, draw the space diagram. So I have draw here that the space diagram, you can see from the space diagram there are 3 steps for the drawing this the you can say for calculating this the connecting rod of midpoint and the crank or the magnitude and direction. So first of all, draw in the 3 step. One is the first of the space diagram, second is the velocity diagram, and third one is the acceleration diagram. So first of all, draw the space diagram, some suitable scales. Suppose 150 mm and 600 we can't draw this in our copy notebook. So we can take the scale, that's the 50 mm equal to 1 centimeter. So you can draw the 3 centimeter. So you can draw here the 3 centimeter 150, right? So I have drawn the space diagram here. After that, from draw the vector OB perpendicular to BO with suitable scales and represent the velocity B with respect to O. The velocity of B is given. So velocity of B with respect to O is the 4.713 meter per second. So from B, point B dash, from point B, draw the vector BA perpendicular to BA and represent the velocity of the A with respect to O. So we can draw the velocity diagram. So first of all, in the previous case, I have draw the velocity diagram. So from we will take the some suitable point O from O to B. So O to B, that is the this one. So V equal to R into omega. So R is given, omega is given. So that point B to O, that point B is known. So velocity of B is known. Velocity of B is known. After that, B to A. So we can draw the perpendicular to this link. So perpendicular to this link, B to A. So that B to A, that this is the perpendicular velocity of B with respect to A, find out, and the slider moves along this. So A to O, A to O. So that moves, A moves to this cut point at some point O, A. So this is known as velocity of A. This is known as velocity of A with respect to B, right? So in some point, midpoint, at the midpoint, so in midpoint we can see that is the D point is there. So connect with O to D. So we can see here how from drawing this we find here, basically you can say we can find here that is earlier case, in the first case only the omega of given is this link BO, but we can see, we can measure here the velocity of B with respect to A, velocity of A with respect to B, and acceleration of velocity of A. So we can see here that the angular again in this link AB, that the two component of the acceleration, one is the radial acceleration and one is the tangential acceleration, right? So radial acceleration, that is A RBA equal to omega square into R, omega square into length, right? So omega is known, omega equal to V into R omega. So here you can measure the value. The velocity of radial acceleration is already known, right? So that's why I am coming here. So in that case, we will draw the velocity diagram. After that, just will see that the velocity of A with respect to O, by the measurement we will find out the value of 3.4 meter per second and velocity of A from the vector. So we can find out velocity of A, these values becomes that is 4 meter per second, and velocity of B with respect to O, that is 3.4 meter per second. These values come from the measurement. After that, in order to this, the velocity of the midpoint D of the connecting rod AB divided in the vectors, in the same ratio you can find out the value of this. So we can velocity of vectors, you can see in the same ratio you can divide it in this and find out the velocity of D. We will find out the vector D equal to, by the measurement we find out 4.1 meter per second. So acceleration of the midpoint of the connecting rod, we know that the radial component of the acceleration of B with respect to O, or the acceleration of B, that is radial acceleration. So radial acceleration again B with respect to O, that is, so you can find out the radial acceleration, velocity of B the square upon O length of OB. So we can put here that the radial component of acceleration A with respect to B we have find out, because we have all the radial we can say the velocity of available all the three links. So one link the fixed, so all three links the velocity is given, so you can find out the omega, or you can calculate the radial acceleration, right? So radial acceleration we calculate, and from after the radial acceleration we have, we can draw this the tangential acceleration and acceleration diagram basically, right? So from the acceleration diagram for draw, so we can draw, you can see here that the O dash, B dash, from here you can see that is the O dash, B dash, this point is the B, right? Velocity of B. From O dash to B dash, take them some suitable point O dash and draw the O dash B dash is parallel to this link AB or BO. Some suitable example represent the radial component, because that one link is there is no tangential component. So O dash B dash the value becomes that is 148.1 meter per second. So we draw the value O dash from O dash to B dash, that draw the acceleration of A. After that, I come to here to here, that is completed, that is no tangential component of this, because OB rotates in the constant speed, therefore there is no tangential component of the acceleration of B with respect to C with respect to O. So now come to the point number 2, from B to A, right? So from A to, we represent the following two components, one is the radial component and another is the tangential component. So the radial component of the acceleration of A with respect to B, that the ARBA. So we can find out from this link we have the two, one is the radial component ARAB, and one is the tangential component ATAB, right? So from B dash we draw the radial component. So radial component we have the value, the radial acceleration we calculated in the previous slide. So you can see the radial component A into B equal to 19.3 meter per second. So from B dash to X dash, so you can draw the B dash to X dash, that the radial component at some point, and it's the B dash X dash is parallel to this link AB. So you can see that the radial component, from radial to tangential we draw the X to A dash is the tangential component, but we don't have the tangential value, only direction will given. So after that, from we can go from O dash to A dash, because the sliders will move along only this one. So there is no centripetal acceleration there, only the slider moves along the A to O. So we can draw this from we can draw the parallel to this. So this O dash to A dash cut at point A point, some suitable point, and these value X A dash and O A dash is cut at some point. This position is known as A dash, and this value is known as O dash to A dash represent acceleration of A, and this X to A dash represent the acceleration, tangential acceleration of link AB, right? In order to say some acceleration of the point D, midpoint D, that the connecting rod divided in 2 points, divided in the same ratio in this velocity diagram and as well as acceleration diagram. So D is the midpoint of the AB, therefore D is also the midpoint of B dash. So you can see in the midpoint A dash to B dash, this point is known as the D dash at the midpoint, and you can measure that the acceleration of AD will be given. So by measurement we can find out the acceleration of AD, that the vector O dash D dash. This the value becomes 117 meter per second, meter per second square. That is acceleration, right? So first is completed. The second is the angular acceleration of the connecting rod. So angular, we know that the tangent angular velocity of the connecting rod. So omega AB equal to, that is VBA upon BA. So VBA, velocity of B with respect to 3.4 upon 0.6. So you can calculate 5.67 radian per second, that is anti-clockwise at about the B. Angular acceleration of the connecting rod, we can see that we have find out the angular acceleration. So alpha. So we have the tangential acceleration of, we have the tangential acceleration ATABA, that is the 103. These values becomes ATAB from this value 103 meter per second square, and these values got from the measurement. So we know that the angular acceleration alpha equal to ATB upon BA. So these values in the 171.67 radian per second in the clockwise direction at the clockwise point B. So we can see here from drawing this, basically the purpose is that how to draw. Basically, first of all, for the drawing any component of the acceleration, we first of all draw the space diagram. First of all, understand the problem, what is the problem given. After that, draw the space diagram. Then space diagram, you can complete the velocity diagram, and after come to this acceleration diagram. Because as from the velocity diagram, why velocity diagram we draw this? So we can find out, basically we can say the radial component of all these unknown points. So you can, here you can find out known radial acceleration of this A. Here the radial acceleration is known. So after that, when drawing this velocity is known, so we have when draw this radial acceleration, so is known. That's why one particular point is known and another is unknown. So we can mix up, match that the common point, and then draw. So I hope you have understand the how to calculate the acceleration. So thank you so much. And further, if you have any query in this velocity diagram, acceleration diagram, and calculation of this, so please feel free to contact with us, and thank you so much.